This is a 2.1 seismic and wind loads. Basically telling you how seismic loads or wind loads come from, at least in the U.S., and how the U.S. code addresses them. The outline is different. The U.S. design codes mostly. I'm going to go over basic design concepts in the U.S. for seismic. R values again. Back to R values.
Yeah.
What do we mean? Seismic loads, seismic load combinations, and then wind loads. So the building code in the U.S. It's the basic building code is the IBC. So that's the whole U.S. Each state adopts the IBC and becomes we have it called California Building Code, CBC.
Yeah,
If you look at it too, it's pretty much the same because they adopt everything from the IBC. So the IBC is the basic standing code in the U.S.
They stopped at 1997.
Yeah, this one is the UBC is 1997, but this is the CBC.
CBC.
Yeah, so it's they just adopt the IBC, whatever it is. Yeah. So now this is the basic code. Doesn't cover everything on the design, concrete design, steel design. They don't cover it because this book. Well, it's pretty thick and thicker, but they don't have they try not to cover all the information there. What they do is refer to different codes for steel design, concrete design, or what. So for steel design, they'll go to or the loading right now. The coding loading is go to ASC for basic loading and R values. For steel design, they will refer to the AISC 360. For concrete design, they will refer to ACI exactly. So that's how it works in this country. One of them, this is the basic code, and from there it references to different types of code for the different materials and loading. So this is how the building code does. So general information when it comes to steel design, the building code references the AISC 360. So that's your steel design. It references them directly. Okay, and here within 360, it references 341 seismic for design, and then in seismic, they reference the pre-qualified connections for special and intermediate. So basically generic, and when you go into each one of these, it gets more specific for the application.
The number after the AISC, meaning the number.
The number after AISC is this their publication. If you zoom in, like this one, there's just a number on there. I don't know how they come out with this number, or I don't think there's a special meaning, but it's probably something for them to keep track of. So, but we know it. People know it as a steel manual. In the front portion is the basic steel property information. Only the back portion is known as the 360 document. So when you say 360, it's not the whole book. It's just the specification on the back. So the 341 is the whole thing. 358 is the whole thing. So that's how steel design, when someone's trying to do steel design in the U.S. is basic code. They tell you what some of the occupancy level and all that stuff. Then you kick it to the ASC to get the loading. Then when you're actually designing the connection or designing the member, then they reference these specific documents. So now, just being more specific, once we get into 341, these are the different editions. So you can see, first edition came out in 1990, second edition 92, and all the supplements. 1990, 1989 is the earthquake, Loma Prieta, up here. Okay, 97 before that was the Northridge earthquake. There's all the supplements that come out before. So you see, after a certain earthquake, they tend to generate a lot more code. So this is the different editions of the AISC. So now, previously, I think there's still every 3 years. Now it's every 5-year cycle. So not as bad. So next one is 2015. The AISC 358 is for the connection. Again, this is a 5-year cycle. So we are in the second edition right now. Like I said before, the IBC design philosophy for earthquake resisting design is the objective is to prevent collapse in the extreme earthquake likely to in a building. It's not like the design objective is make sure the owner could make it operational or open up the business right away after an earthquake. No, the design objective is to basically collapse prevention, life safety, the same thing. We don't want it to collapse and kill the people. So that is the design intent. So not to limit damage, not to maintain function, and not to provide easy repair. Okay, so the remember, that's all the basic code requirement. People do go further to, okay, if their business is very critical, or if the business, or not business, but if it's a hospital, if it's a fire station, then they go into this a little bit by designing it to be more stringent. So they would basically maintain function, limit damage. Not many people go into easier repair. The last project that I worked on before I joined Simpson is for Genentech. It's fabrication, the Genentech drugs. They wanted to be able to move back in 7 days and fully operational. So 7 days fully operational. So the building had moment frames with dampers. So best of both worlds. They spent a lot of money on trying to get that up. Okay, that's that. So owners could go more than this basic requirement, but the more you go, the more costly it becomes. Okay, ductile design. So what does it take to prevent a building from, let's say, collapsing? I mean, we know the earthquake. No, we don't know when the earthquake is going to come, I would say, and we don't know how big the earthquake is going to be. So the thing is, you want it behavior to be ductile. You don't want it to be so brittle, a little bit movement that then collapses. You want to be able to sustain a lot of cycle movement without collapsing, and that's the major concept is to design it for ductile behavior. So ductile behavior, here's what the ductility means is, you could go, this goes a little bit further when you push on it. Let's say OMF here, IMF here, SMF is here. So you push the H here, and the deflection, you're supposed to be able to get a lot more here. So this number, the wider the range is better. So this is kind of yield, when you structure yield, and that's your ultimate deflection. The two divided by each other, the bigger the number, it's better. So that's the ductility. Definition actually is here it is, the delta yield, delta failure. And when you look at it, ductility factor is delta failure divided by delta yield. So when people say in concrete, you might have seen it, ductility 5, ductility 6, that's what they mean when you start yielding. And then when is the final failure mode, when the two numbers, what is it? You divide it, you get a ductility factor. That's how they mean. So
we have FU and F1.
Yep, we'll get into that. This is the FY value here. This is simplify actually. FU actually, when you go up like that and then drop down, the top one is FU. Yeah, so we'll go into that when it gets to the materials for steel. But ductility versus strength. Typically, the higher the ductility, the less strength is required, the less loading. What I'm saying is, it's a little bit, I wouldn't say contradictory, but that's what it is. The higher the R value, you get the design for smaller of the seismic load, and they give you the benefit of that. And that's why all these strength and ductility requirements are important, because you're actually designing for less load. So how do you develop ductile behavior? Is, okay, you choose the frame element, the fuse, the yields in an earthquake. So beams and moment frames, braces and concentric brace frames, or links and eccentric brace frames, and then detail these fuses, make sure they could sustain the inelastic deformation prior to fracture and instability. So you have a detail for that, and then you design all frame elements to be stronger than the fuse. So we design a column, we design the beam, and design whatever part of the connection that's not yielding to be stronger than that. That is the ductile behavior, and that's the concept. In concrete, I think it's very, very similar. They force you to do the plastic hinge first, how much strength you have, then you design it around it. And in concrete, detailing is what most of the stuff that comes into play. So where do you see these fuses we're talking about? What are fuses? Fuses in typical frames are in here, in the beams. We saw the connection or the testing. You'll see how they're yielding. That's what they consider fuses in the beams. And also the bottom, if you have a fixed connection. In braces, they're typically in the brace. Okay. In these are called this one is an eccentric brace frame, because when the two comes together, this link here is eccentric, doesn't meet. Okay, so these are fuses, and as well as the unbonded braces, you'll see these are the braces as well. So these are the fuses, and for us, that is our fuse. Okay. So when I say what is ductile behavior look like I said, it's mostly from people could tell after you test something. I mean, some from experience probably say, oh, that's not ductile, that's ductile. But actually, these are from test results. You could measure, you could do your delta U divided by delta Y. That's how you could do it. But in order to be able to do that, you need to do the testing. So here's a more ductile behavior, versus this one is less ductile behavior. Okay, they might be able to get to the same point, but the loops are not as full, and these are flat versus the full loops. Okay, so that's more ductile and less ductile behavior between the two. So just to hammer it in again, R values in the code are related to ductility. So the two, they're trying to tie the two together. Not quite one-to-one, but that's the concept. Is more ductile, you get a higher R value.
Yeah.
So R value is, I talked about this, the ability to absorb energy without collapse. And the same slide, I just want to hammer in, more higher R value, the more ductile the system is. Less ductile, you get a lower R value. Okay, so if you look at these ones, so the higher the R, steel plate shear wall 7. Buckle brace, restraint brace frame 7 or 8, depends on how you do it. Ordinary concentric brace frame 3.25. That's probably the lowest on the list. Okay, 8 is for the special. So you could tell by the system they use and if they're ductile or not. Okay, just by the R value, because they are related. So what do I do with these R values? Okay, as engineers, okay, I know we have these R values. These frames are ductile. But how do I incorporate it into my design? Where does that come into play? And just to point out, what we were looking at is actually from a table in ASCE 7. You know, it's 12.141. And these are only for seismic design. And they list all the R values, what it is. So you choose a system, and then each system you choose is got the R value that's associated with it. So for a wood shear wall that you're designing a residential with plywood, R of 6.5. Okay, that associated with plywood. So the R comes with it. Okay, so now the R is used to calculate base shear. So base shear, here's this certain factor, and that's the total weight of the structure. Okay, so that's the building weight. So for CS, it's just a ratio of something that they give you, and you have to go through each step to calculate. But if you look at the CS, the R value is on the bottom. So the higher the R value is better. It's a smaller CS, the less force you design for. Okay, so SDS is actually this term is related to I would say a response acceleration, site dependent. So the worse, the more earthquake that frequent zone, then you'll see a higher SDS value. Okay, it's related to location, geological location. West Coast, you see those high SDS values. East Coast, small SDS value. And these are all in the SDS, SD1, S1. All these are published in maps. And we'll show you what those are. The IE is the seismic importance factor. The T is the building period. Like we said before, for your hospitals, police stations, the IE, they make it a lot bigger. So if the flip side, you multiply that number, it becomes 1.5. The side in the hospitals, basically you're 50% more force compared to anything, compared to the I of E of 1. Okay, so just hammer it out. Bigger R value, smaller design base shear. Seismic base shear is only a portion of the building weight. So when we see CS, this number is always less than 1. Okay, typically it's about 0.2. 20% or so. Okay, it might be more, might be less, but typically that's what we're designing for seismic is 20% of the weight. Okay, so I'll show you a design example now just to hammer in these points, how we get these or how engineers actually go and get these. So the short periods, it's from a certain equation in ASC 7. You take 2/3 of the SMS. SMS again is some equation, you get it. Yeah, S is the map spectral acceleration point to. These are looking up from the map. So you plug in this term, you get it. You know what FA, look it up, and then you plug in this, then you get the SDS term. Okay, I'll walk you through it. It's actually a website that does all this for you later. FA is a short period. Side coefficient from the table. Long, we covered the SDS. Okay, short period. Now you have to worry about the long period. Structures could be short period or long period, and depends on where you are and how tall you're building. It could be controlled by one or the other. So they're trying to cover both ends. That's the same equation, very similar to where they are, and just look down again. In 1 second, you also look up from maps.
You use the UZS software.
Yep. That's exactly USGS. Type in the zip code, and you get all this information. Exactly. So this one is directly from the back of the IBC or somewhere in here. So you can see all these different acceleration SS values. You could look it up here, but I really couldn't pinpoint anything. So that's why they developed the USGS, the tools for engineers to use. So if you're designing it here, pick a value. It varies quite a bit. Just within a certain zip code, you could get different values. So all these published values are based on a certain site class. So there's some modification required, and they are given for a 2-second period. Damping, 5% damping. I'm not going to cover that, but that's just the basic default of what it is. These maps are from the USGS. So there's the website if you need to go and look at this one. The S1 value as well. I just did the SS and S1, so they're both 1 second and short. SS and the values. Here's the US. You're here, California. You can see these are the acceleration. Hot all west. Some minor areas up here, but this region and that region, and as well as Hawaii somewhere, you get some high acceleration. So Hawaii is there. So anyway, the coefficient, I mentioned it before, is also from the table, and from the table that is based on site class. Now site class is related to not where you are, but actually the soil. Exactly. So soil might, we could be living in Pleasanton. My site could be a lot worse than yours because of the soil condition, and so they try to take that into consideration when they're calculating the seismic load. So site class is typically determined by your geotechnical engineer. They have something in chapter 20 to help them determine it, but these you typically get from your soils engineer. And the typical default, if you don't have anything in here, is like everybody assumes D. If you don't have a source report, anything, just assume D is the worst. Okay. IE, the importance vector I mentioned before, this is tied to the risk category. So 1, 2, 3, 4 depends on where you are. If the risk category is related to your occupancy level, 1.5 for occupancy level 4, and that's the important structures. Show here, risk category 1, 2, 3, 4. Building structure designated as essential facilities, you get a 4. Everything else you get 1 for the barn or whatever, but 2 is typically the residential. So that's what the different risk categories are. So building period, this is the equation from the code, and is the approximate equation based on what systems you use. So HN is the height, and then C sub T and X are directly from this table. So for us, if we have steel moment frames, then your C sub T is 0.028, and then times 0.8, so you get a approximate period of the structure. So here's an example to determine the base shear. So given we have a residential building, pretty damn tall, I guess, 20 foot, with SMF, category seismic category 2, R for 8. If you plug in those numbers, okay, I just put in the home office location. Here is the latitude, here's longitude. I just use this website, Google something, it looks like a French website, that they'll give you the actual longitude and latitude. So I just type in the address and they convert it to both the longitude and latitude. And once you know that, I assume a class D right now because we don't know the source reports. And then the weight of the building, that's calculated. That's not something. So the problem is to determine what is the base shear for this given structure. So that's what engineer does every day. Given these informations, the easiest thing is, okay, first step is determine SS. This is the USGS website. You put in the code that you're designing for. I just title home office, classification D, risk category 1, 2, or 3. They don't really distinguish it. No, site latitude, site longitude, and then you say compare values. It will give you this. This is the location to get this map. So if you know it already, then that's good. So the output, pretty good. They give you the MCE response, design response, all these outputs here. Okay, I'm blowing it out here. So SM is this, SS is that, SMS is that. They give you S1, the 1 period, and then SM1. So inter risk categories D, since SS is greater than 1, FA. I'm just checking, make sure we're getting the output. So FA goes FSS, so put in 1 times 2.104. So the SMS should be 2.142. So there it's correct. Okay, so SDS is 2/3 the SMS. So 2/3 the SMF is 1.428. So is 1.428 somewhere? Yeah, 1.428 here. So that's the numbers are correct. Okay, so now knowing these numbers, I have to plug it in to get my base shear. So here's the IE, here's the R, and here's the SDS. So let's do the plugging in these equations. So first one is 1.42 divided by 8 divided by 1. So 0.1785, okay? First equation. There's a minimum and there's a maximum. So we can't, this is the maximum I'm calling. So 1.482 divided by 0.308, the period, that's where we need a period from. And then 8 divided by 1.57. So the maximum is about 0.56 or 0.58. What we have now is that. So we're not over the maximum, so that one's still okay. The minimum, what I call this one is minimum 1, so it's 0.004 SDSLE. Get 0.00628. So you have to design for a minimum. You can't go less than that, and you don't have to go more than this one. However, since our S1 value is greater than 0.6, we have to check the second one as well. So the second one is actually becomes a less number, a smaller number. So at the end, our CS is 0.1785. So somehow I have red color in mine and doesn't have red on that. I don't know, I think just the projector. So that's how you determine and get a seismic load from the US code. These are the different steps. I kind of walked through how to get it. So finishing it out, V equals CS times W. With this one, your base shear is 14,280 pounds. So that's seismic load in the US. So please note, V is different for each direction. Okay, I calculated assuming an R of 8. In a direction, if you have a shear wall, then you have to calculate it for that direction as well. So typically they call it north, south, east, west. Then you have to calculate it twice.
So the R value is each affected.
Yeah. So yeah. So VS, what we just did is in one direction. If I plug back in the different R, like here, R of 6.5 instead of 8, 6.5, we're gonna get a higher number. So yeah, so if you plug it in, I think you get about 20-some percent, 0.02 something, or 6.5. So that's the seismic code. So that's E from the ASC 7 earthquake load. So also you have other loads to deal with. The dead load, live load, roof live load, rain, snow, or wind. Wind could be lateral or it could be sucking up the roof.
The
So
weight of the building W is dead load, whole dead load.
yeah, the weight of the building is the dead load, like how much this weighs. Live load is people walking around or whatever people. So roof live load is on the roof. So they'll tell you what to know. And the building code has minimums for a lot of these, and you just typically go with that. Dead load is what engineers probably determine, and they add up on the materials. My tile is so thick, here's so much how heavy you get it, you assign it some value. So that's how you do the different load combination. No, earthquake load, we just determine what the earthquake load. So that V is the earthquake load. Okay. There's also the lateral earth pressure and groundwater. We won't be covering these because it just for foundation wall or some other earth pressure into your structure. The frames are not going to be seeing this, so we won't be having this into our load combinations. So basic load combinations from AAC 7, these are directly from AAC 7. You have this 1.4 dead, 1.2 dead. What they're trying to do is they just get some load combinations, make sure that you cover your bases in terms of, okay, I assume all the people in this place, okay, my earthquake can happen at the same time. If I have a party on top, what's the probability of that all these going to happen at the same time? So they have different load combinations to cover different conditions. Okay, so you have basically 0.8 W, 1.2 dead. Then all you need to do is half the live load. So there's just a lot of variations to cover it. I never question it. Just go through all the different combinations, expand it, and in the Excel spreadsheet I showed you before, that's where we got the L60 to the 64. Is expanding all these plus or minus equal or to get these the 60 combos. Okay, so that's has already been done. What's important here is the combos including E. So we have that 1.0 E, 1.0 E, and then a dead, and then the dead. So low combinations with E is you have the row SDS, basically vertical acceleration. So you have to add that to your low combination. So also this is the 0.9 dead. If you analyze the frame using the first combo, the compression column is that combo is going to govern because it's a lot more heavier. But tension is going to govern by this combo because you can't use all your dead load to resist tension. So you're going to see higher on from these combinations. Okay. So again, rho is the redundancy factor. It's typically 1.3 or 1 unless you meet certain conditions. So there's only two numbers, 1.3 or 1. Yeah. So QE is the horizontal seismic force only, so the one that we just looked at. And EV, I substitute that in here already, so this is supposed to be, the whole term is EV. EV is the vertical seismic effect. So this term, that term is a seismic effect. So seismic, not only horizontal or vertical, but they also record up and down. Yeah, so that's vertical. So some records do show vertical, and they're trying to capture that by putting in 20% of this. Okay. Substituting E into the basic low combinations, you get this combo for seismic design. Okay. And then another one for the substituting that into this one, you get that in that combination. For amplified seismic, ASC7 has the amplified seismic, remember the omega?
Yeah.
Omega. So this one, you basically, E is this, you plug in this whole term into E, and that's what you get. Okay. E is that, you plug in this whole term into E, that's what you get. So basically combining these two equations, you get this one. Combining these two equations, you get that one. So that's the amplified seismic. Omega naught, where we mentioned that before, R, omega naught, C sub D. These are always go in hand, like it has to be a whole system when you look across. You cannot choose R of 8, choose C sub D of 3. You have to go this way when you're doing the calculation. Okay, plywood shear wall is this one, and R is the modification, response modification factor. Omega naught is the overstrength factor. I'll tell you what that is a little bit later. C sub D is the deflection amplification factor, and it is used for deflection check. For drift check, you use that C sub D term. Amplify low. The amplify low omega E it's intended to provide an estimate of the frame's ultimate or plastic capacity. So design low is always elastic. Your design is always in the elastic range. Okay, but what is your ultimate low? Is they want to make sure that you're considering that in your design for some other elements. The omega E combos do not apply to every situation. Remember the one that I just showed? These do not apply to every situation. Yeah, only certain locations. Like for our base plate design, they require you to have omega combo. And for we have anything that's like a wall or another frame sitting on top of the frame, but it's not on the column. So this continuous systems, they call for the amplified seismic load combo. So this is only occur in certain situations. So you don't apply it to all of them. And at those situations, they would like to know what is the ultimate that your system could deliver, and that's why they have these omega and Q sub E values, is to estimate what the frame's ultimate capacity is. So why amplify seismic load? Okay, as all seismic loads resisting systems demonstrate through inelastic behavior. Okay, they are designed to form a fuse at certain locations. To account for this behavior, the overstrength factor is used. Okay, we designed it to be elastic, but knowing that the system is actually inelastic, how do you tie the two together? Okay, the VS and ultimate low, that difference or that ratio is your omega overstrength factor. So I have a chart somewhere that shows it graphically a little bit better. So specific components and beam column connection must be designed to remain nominally elastic, while the fuses are designed for amplified force. So that's basically the U.S. seismic design condensed. I saw you hear a little bit about all the earthquake things. I'm not going to go talk about earthquake. How do we get from that to spectra? But the basic low combos, I think that's all you need to cover at this time. So anyway, that was seismic. We cover wind. Unlike seismic loads, like I told you before, there is no reduction value or no R value for wind loads. So whatever wind load, whatever pressure that you think that's going to happen, you're designing for that force. It vary, depends on the height, depends on location. And I'll cover that quickly a little bit later. But we don't reduce the wind load per se for your design. Okay, so wind loads are based on pressures on the building, and the pressure on your building depends on if you're on a hill, on a ridge, the wind effects going over it. Building geometry, if you're round or you're square corners open, that's part of it. The ground roughness category, wind speed again. This is where you get it from the wind map. It's kind of like seismic. You've probably seen that somewhere. Wind directionality, exposure, gust factor, building height. So building height is important. Depends. The higher you go, the higher pressure. But also, number 4 here is IBC 2012. All the wind loads now are at the strength level. So keep that in mind when you're doing it. For the wind loads in ASC 710, there are 4 procedures you could use to determine the wind load for the wind. They call it main wind force resisting system. So the direction procedure, envelope procedure, directional procedure for building, like rooftop, chimneys, anything that sticks out, and then the wind tunnel procedure. Not many people uses it. These are for like critical projects, high rises, whatever. Yeah, so they're high wind, and they go do some wind tunnel testing, and then to see what the wind loads are. But for ours, it's typically chapter 27, and then the chapter 28 low rise. So for chapter 27, this is the pressure, velocity, gust factor. Like I say, all these comes into play. Roof height, into calculating the wind load. So, and all these again is from different sections and different tables within ASC 7. For some of these, I just know that the sections, I'm not going to go through it, but to calculate that for windward walls, and leeward walls. If you have a wall in the front where the wind's hitting it, or where's the back, pressure is distributed and different, and when you're calculating it, the different height assumption, you have the different height assumption they give you, and also you have positive pressure and negative pressure depending on where you are. So in each one of these, they ask you to calculate, assume a certain height to evaluate these loads are. So the V is basically the velocity, D is the directionality. This is a topographic effect. So these are factors, just published factors. You could look up directly. You don't have to do much. The wind load is you look up from the map, and then you get a pressure basically on your building, and that's how you get these loads. So here's the wind map. Different miles per hour. I think there's even ATC's got a better one. You could kind of like what we did for seismic. You punch in the address, it'll give you the wind speed. Okay, so you don't need to find out what they are, like looking at the map to be more specific. I think you have to type in the address, and just like the seismic one, they'll give you longitude, latitude. You plug it in and zoom. Here's your design wind load.
So this is the 2012. This is the newest.
Yeah, this is this. I don't know where I got this map from, but that's something. The wind region. There's actually got a presentation from Shane, I think. So I'll just combine some of these things. So wind loads on the frame. For what you guys will see, typically you'll see point loads at the node, and then you just apply your wind load, and then the wind loads typically go more higher, or higher loads when you go up the building. So, but for frame analysis, we typically lumped it at each height. You could put it in either as a distributed load or each node, either way how you apply it, but it's just higher when you go up higher. It should be. So review. IBC is the basic building code. ASC 41 is the seismic revision is referenced by the building code. Objectives of building code is life safety for earthquake design, and then to prevent collapse during a major event. Ductile design is required. More ductile the system, the last seismic lateral has to be designed for. Typically, structure designed for lateral seismic less than 20% of the building weight. Yeah. Wind loads have no ductility value or no R values. Designed for actual pressures, the portions like the seismic. When I say portions, the percentage of the building weight. That's it for the loading. So hopefully you guys get some background in terms of, you don't just see the number. Somebody will give you E. How did they get the E value from the site and all that stuff? Let me start recording.